SAFOD is a scientific drilling project, and this project was designed to understand the processes that control faulting and earthquake generation along the San Andreas Fault. The acronym SAFOD stands for the San Andreas Fault Observatory at Depth, and this observatory is located at a very unique site along the San Andreas Fault in California, at the transition from the creeping segment of the fault to the northwest of the site, from the locked seismogenic portion of the fault that's to the southeast. This drilling project is really critical because, unlike weather patterns, we can't directly observe an earthquake when it begins, because this process occurs on a fault zone deep within the crust. Drilling into the fault zone is the only way that we can bring rock samples from the heart of the fault up to the surface to provide samples for scientists to study. The rock samples that we acquired from drilling into the San Andreas Fault are extremely unique, and they're as important to our ability to understand earthquakes as the moon rocks are to understanding the history of the moon and the early history of the Earth. Drilling began in 2002, and this started with a pilot hole, a vertical borehole to about 2.2 kilometers depth, designed to test our drilling capabilities in this rock type and also to test our geophysical instruments. The main borehole was drilled in 3 phases. The first phase was drilled in the summer of 2004, and it started at the surface of the Earth, went down vertical to 1.5 kilometers depth, and then bent toward the San Andreas Fault and ended right before it got to the fault at about 2.5 kilometers depth. The second phase of drilling occurred in the summer of 2005, when the borehole crossed the San Andreas Fault into the southeastern block, passing from the Pacific tectonic plate into the North American tectonic plate. The third phase of drilling occurred in the summer of 2007, where the goal at that point was to kick out of the side of the main borehole and drill a multilateral, and while drilling that multilateral across the San Andreas Fault at a shallower depth, to also take a continuous sequence of core of the 2 creeping segments of the fault. The samples that we brought to the surface are cylindrical in shape, and they're about 10 centimeters in diameter, and we refer to these as rock core. The borehole intersected different rock types along its length, and this is an example here of the rock type that was encountered in the upper reaches of the vertical portion of the borehole. As we got closer to the fault, we saw a greater density of fractures in the rock samples, and then when we got right into the heart of the fault, we recovered rock samples that we would refer to as gouge. And gouge is a rock type that is really composed of ground-up particles of a host rock or parent rock. This is an example of the southwest deforming zone, the actively creeping zone, and in this sample you can't really see any particles because they're very fine. They're micron size or even smaller in diameter. The central deforming zone, the one that is creeping at a faster rate, is illustrated here, and you can see different colored clasts within this gouge sample, and these clasts are actually representative of the original parent rock that haven't been ground down, but they have been sheared as this zone is creeping, and they've actually become aligned during that shearing process. So to understand the orientation of these clasts after shearing without cutting into the core, we were able to run it through a medical CAT scan machine and get a 3D visualization of this sample. The hotter colors are indicating where we have clasts, and you can see that these clasts have different sizes, but in general the shapes are all very similar, and the shapes are an artifact of the shearing process. The core samples are extremely unique samples of rock because this is the first time that we had ever transected a plate boundary fault zone in the continental crust, crossing a plate boundary fault and collecting an entire suite of samples that represented those plate boundary processes. So these are samples that scientists from all over the world want to study. The Gulf Coast repository that houses the samples is in charge then of distributing those samples to these scientists so they can perform research, again, to try to understand the fundamental processes of earthquakes.
I was interested in SAFOD material to try and learn how the fault behaved frictionally, whether it was strong, so You can think of this as pushing a box across sandpaper, or whether it was weak. And you can think of this as pushing a box across ice. And to do that, I needed material from the fault at depth, and that led to my involvement on site to get both the cuttings and the core. Once I got those samples, I took them back to my laboratory and used an experimental apparatus at Penn State to shear these materials. What we found was that material from the fault was very slippery and very weak in terms of its ability to resist shear. And what was interesting was we found that this was highly localized and very sharp area within the fault only, that if you move less than a centimeter into the rock next to the fault, the properties change completely. It's much stronger and behaves more in the sandpaper box type fashion as opposed to ice.
Our goal is to produce earthquake ruptures in the lab that can reproduce features we see in natural samples. This is a sample from one of the SAFOD cores, and we've prepared it so we can look at it under the microscope. And we can use regular transmitting light, or we can use filters like this one to enhance features within the sample. With this filter, you can see this blue section very clearly. This blue section is a region of smaller grain sizes compared to outside of this section in sort of the purple and reddish areas. Those areas have a much higher grain size than within this section. This is what we call a principal slip zone, and it's a feature of earthquakes. It shows the region where during the earthquake rupture, as the faults are propagating, the grain size was reduced dramatically. We want to simulate an earthquake rupture in the lab and try to reproduce features like this zone in our samples from the laboratory. This is important because the theories and hypotheses we test are used in earthquake models. And by verifying these hypotheses and theories, we are helping to improve models that can hopefully one day predict earthquakes.
There are a lot of different types of analyses that are being done on these rock samples, trying to define the geochemistry of the materials, trying to define the processes that governed their deformation, trying to use the samples to simulate earthquakes in the laboratory, and trying to extract organic material from the samples to try to determine whether there was a heat signature left behind after an earthquake occurred within these samples. One of the reasons that this project is really important to me is I've spent a lot of my career studying fault zones at the surface of the Earth. There's always a question when you study samples at the surface that were deformed sometime in the past about what they can tell you. That leads us to this project, the SAFOD project. It was a golden opportunity to actually go into the heart of an active fault zone at depth where earthquakes actually start to form and pull rock from that system and bring it to the surface and study it before it could ever be altered or modified with time. That's what makes these rocks so special. The SAFOD samples are a real scientific treasure. We've already learned a great deal from studying these samples, and as new questions are posed and new technologies are developed, there's a great deal more that we can learn from them.